Namaskar, my dear friends. Let us design a microcontroller system circuit. So what we'll do is, in this particular system design, we will consider F2839 F280039 CSPM, that is 64-pin LQFP package. And this is a microcontroller from C2000 series of Texas Instruments. Okay. So the blocks that we will be designing is like power supply, safety and protections. Then we have power supply management. We will be having this as a microcontroller symbol, and the various peripherals that will be connected is like we have potentiometer ADCs and PWM, we have ADC measurement or ADC monitoring, then we have CAN transceiver, LIN transceiver, we will have temperature sensors like humidity sensor and temperature sensors, then audio buzzer will be there for alarm beep or something like that. We will be having DAC output also. Then we will be having I2C communication as well, so that we can store data to EEPROM memory. We will have external interface to drive daughter cards or something like that. We will have some IOs representing deep switches, push buttons, LEDs. We will be having one interface for UART to USB, so that you can directly connect it to your computer as well. And this is the programming part that is going to happen, like MCU reset and as well as JTAG programming. Okay. So basically what we are going to do is in this particular microcontroller system design, we are going to consider C2000 series microcontrollers, and at the same time my target MCU is, as I told you, F280039 CSPM. So we have 64-pin LQFP package. As you already know that this particular series of microcontroller can be used for various applications in motor drivers, EV charger, solar inverters, drone applications, or various appliances like fridge, washing machines, like wherever there is a motor application that is needed. Okay, all right. And just now I explained you the block diagrams that we are going to see in that particular system design. Before that, what we'll do is we'll quickly go ahead and see the website of this particular like microcontroller that is there from Texas Instruments. So if you type TMS320F280039C, you will have this particular page. So as you can see, you have the data sheet, user guide and everything, and this is the block diagram from the data sheet that is there. Product detail, if you want to go ahead and see, you can see that what is the maximum frequency that is allotted is 120 megahertz. We have flash memory. This is better than 280037 series. Okay. And this is how we have, like a sigma delta filter, PWM channels are there, total 16 channels. We have functional safety compliant. That is the best thing. Okay. If you want to like design and develop, then we have the design and development hardware board as well. So you can see we have this particular board that we have been using for our various application development or something like that, that is called as launch excel F280039C series. Okay, so this is just costing around $40. Okay, so if you want, you can have a look into this particular board. If you want to order this particular components, you can have like packages of 64 pin, 80 pin and 100 pin. What we are right now giving you the application is based on 64 pin, that is F280039C SPM microcontrollers. All right, so this is having 64 pin LQFP package, and as you can see, this is the like launch pad that is there from Texas Instruments for this particular series microcontroller. However, this particular microcontroller will be having 100 pin microcontroller onboarded on this particular board. Okay. All right. This is the data sheet of this particular microcontroller, where you can see we have a list of like applications that is there: motor drives, appliances, hybrid electric or powertrain systems, solar and EV charging. We have digital powering like buck converter or something like that. We have body electronics and lighting like infotainment cluster and all. We can utilize this for test and measurement equipments as well. If you want to see applications in detail, you can go ahead and see these are the applications that is there, that we have already explained you in various other videos. Then we have applications from here as well, like three phase UPS and single phase UPS and all those things. Alright, so with this, what we'll do is we'll directly get into the circuit design that we have to look forward. Alright, let's get started. So what we are going to do is this particular block diagram we will be seeing one by one. So what is the approach of designing a circuit is basically first design out your microcontroller symbol, and then you design your power supply requirement for this. Then you design your decoupling capacitors for the power supply pins, okay, decoupling capacitor, and then you design your programming part. So this will complete your like microcontroller essential schematics, and after that, as an as it is required, what you can do is you can add different peripherals. So let's get started. So I am going to show you the microcontroller part. So this is the symbol that has been designed for F280039 CSPM, and you can see we have GPIOs. You can see GPIOs arranged towards left side. We have ADC pins towards right side. We have JTAG pin, put it here. We have like a ground pins here, and we have power supply pins above. Now if you see, we have VDD/IO pin that will be requiring 3.3 volt. So that is going to have decoupling capacitor at this place. Okay, VDD/IO, these are the decoupling capacitors that is there. Similar to that, we have VDD pin that will be taking power supply from VDD/IO only. So what I have done is V regulator NZ is grounded directly. So I want to use internal regulator. Okay. And then we have reference pin that is V reference high, and we have analog pin that is VDDA. So VDDA is also taking from power from here with a decoupling capacitors of 2.2 microfarad. Okay. Coming back to the JTAG part. So JTAG part, this is the programming part that you can see here. So you can see we have TMS signal, TCK signal, TDO signal, and TDI signal, as well as reset signal. So that is connected here at this particular 10 pin connector of 1.27 mm pitch. Okay. So you can use this particular like connector for JTAG programming. We have reset switch, so you can see whenever this gets pressed, so manual like reset of this particular microcontroller can be done by this particular push button switch. Okay. So this was all about like essential circuits that was needed. We have V reference DAC that can be utilized for V reference for ADC also. So what we have done is, this is my V reference pin for VDAC, and we have V reference same for V reference ADC. All right. Coming back to the pin mapping, so these are the PWM pins that has been taken as a pair, like 1A, 1B, 2A, 2B, like that, up to 7A, 7B. If you want, you can use up to 6A, 6B, because two motor drivers can be driven by 12 PWMs very easily. Then we have like fault signaling. So fault signal 1, fault signal 2. So since we have two motor drivers, okay, so we will be having two fault signal. And then we have CAN transceivers. So you can see CAN TX and CAN RX is there here. Okay. Similar to that, we have I2C communication, I2CA SDA and I2CA SCL. At the same time, what we have done is we have used like a LIN and SCIA also. Okay. So LIN transceiver as well as SCIN, that is nothing but your UART also. So it is having UART capabilities as well, or serial communication interface as well. Similar to that, we have put user push buttons. So user LEDs. So user LEDs, LED 0, 1, 2, and then we have deep switches 0 and 1, and we have push buttons 0 and 1 for various applications or indication purposes. Okay. Or maybe some interrupt reading, or maybe like configuring up your IO pin for 0 state or 1 state. So deep switches will be very, very useful at that time. Coming back to the analog pin side, so we have like DAC A output and DAC B output. So two DAC outputs are there for applications that you want to have. Then we have temperature sensor on board. We have temperature sensor and humidity sensor also. One more. Then we have potentiometer for analog like voltage purpose. We have voltage monitoring, ADC VCC and ADC VDD. we have shunt U, shunt V and shunt W, that is nothing but your current sensing individually for the three phases U, V, W. If you want, you can have like a single current sense resistor. So single current amplification is done by this one. Then we have over voltage temperature sensing. So over voltage temperature sensing of the like IPMs or any places that you want to have. So this is the way my microcontroller pin has been assigned. All right. So this was all about microcontroller section. If you want to have what I have done is I have put two connectors as well. So these two connectors can give you the 6 PWMs. If you want to increase the number of pins, you can make it up to 10 pins so that fault signal and VOT signal also can be incorporated. So as we have done this thing in our other boards, so you can do that as well. Going back to the next part of the circuit, so this is the discrete part as I was talking about like audio buzzer just for alarm purpose, like ting 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 sound it can give you, so that like you can have an understanding, okay, we have some thing to attend, right? So this will be taking 2.73 kilohertz PWM. So this PWM will be of 50% duty cycle. All right. Coming back to the EEPROM. So let me increase the size. So EEPROM, this is 4 kilobits of EEPROM that has been used from microchip technology. And we have I2C SDA and I2C SCL, right? So this is how it is going to communicate to the EEPROM. All right. Coming back to the temperature sensor. So onboard temperature sensor, I told you. So this one can be giving you the output voltage of 10 millivolt per 1 degree centigrade. Okay. And this is how it is going to my microcontroller ADC of C2000 series that we are designing, right? Coming back to the voltage monitoring part. So this is the voltage monitoring part. What happens is we have 5 volt on the system. So 5 volt is being like a voltage divided Vx, and this Vx will get buffered, then filtered, and then going to go to my ADC pin. Similar to that, 3.3 volt is also there on the board. So this 3.3 volt will be also like divided as a voltage division, let's say Vx1. And then this Vx pin will be going to go to buffer and then filter, and after that ADC pin of microcontroller. Coming back to the other part of like we had talked about potentiometer as well. So we have one potentiometer connected to 3.3 volt and the resistance variation, let's say Rx and Ry. So based on that there will be a voltage difference here, and this voltage will be going to my ADC pin. So this is how a very nice application of potentiometer can also be like verified. Now let us move to the next part of the circuit. So what we are going to talk about is we have IOS pins. So as I told you, we have two push buttons, push button 0 and push button 1. Okay, so you can see user push PB0, user PB1. So whenever this push button is pressed, what will happen? This will get grounded. It means the microcontroller will see a 0 on that. So that will be whenever microcontroller sees low, you will understand that okay, push button has been pressed. If it is seeing high, then what will happen? Push button is not pressed because 3.3 is directly giving it high. So similar to that, push button 1 as well. We have deep switches. So deep switches, left side it is open and right side it is closed. Okay. So if you press right side, then what will happen is the microcontroller will see a 0, 1, and whenever it is open, microcontroller will see it 0. So you can have almost 4 options: 0, 0, 0, 1, 1, 0, 1, 1. So based on these like options, you can have a proper decision making. We have three LED connected, user LED 0, 1, 2, and they are not consuming current at all because they are just driving the MOSFET to make the circuit complete. Okay. So what we are going to do in this particular thing is whenever my microcontroller goes high, microcontroller GPIO goes high, the MOSFET will switch on and the LED will glow. And whenever it goes low, then what will happen? The MOSFET will turn off, and this is how my LED will turn off. So this is a very nice example of LED like interfacing to a microcontroller pin. Now let us talk about a very nice example of my temperature sensor and humidity sensor. So this particular IC is taken from Renesas. So Renesas HS4101. So, okay. So this is inbuilt with a temperature sensor as well as humidity sensor, and you can see those two, like signals are coming and getting buffered and then filtered, and after that it is going to my ADC pin of humidity sensor and temperature sensor. So humidity sensor and temperature sensor is very nice, like a application on any kind of motor driver or any other thing where there is a temperature sensitivity requirement or temperature monitoring is needed. Coming back to the next part of the circuit, we have CAN transceiver and LIN transceiver. So CAN signal is coming from microcontroller, controller side. Then we have voltage translator. So this voltage translator is converting the incoming signal 3.3 volt to outgoing, this signal 5 volt level. Okay, so 3.3 volt to 5 volt level we have converted it. And then this is the CAN transceiver IC that has been used. So this CAN TXD and RXD will be converting this CAN transceiver signal to CAN high, CAN low into this particular connector. This has been, like properly terminated as well, and then filtered as well as ESD protected also. So you don't have to worry about ESD protection and all those things. Alright, so this is very nice example of, like CAN transceiver IC and how it works. So we have CAN transceiver signal coming from microcontroller, and then it is going to like convert it to CAN high, CAN low signal of the CAN based system. Okay. Similar to that we have LIN transceiver. So in LIN transceiver, what is going to happen is we have LIN RX and LIN TX signal. So that is going to get connected to my RXD and TXD. And this particular LIN transceiver is going to convert to my LIN bus. So LIN bus is actually filtered and ESD protected. And this LIN bus is connected to my pin number 1 of this particular connector. So this is how you are going to take this out. If you want, you can do one thing. The power supply, same power supply 12 volt can be utilized to power up this particular IC, and this is how it is very easy to do that. And here it is a clamping diode as well. So this clamping diode will like serve the purpose to protect the IC supply pin. In this particular CAN transceiver, if you want to use, what you can do is you can connect one CAN transceiver, this CAN standby mode. So one of the microcontroller pin, you can connect it here, so that whenever you want to make it work, you have to pull it low. Okay. Otherwise, what you can do is, instead of doing this separate microcontroller pin, you can directly ground it. Okay. So directly ground it, so it will always be working. Coming back to the most important thing that is there in the microcontroller system design is power supply design. Okay, so in power supply design, as we have been talking about various power supplies earlier as well. So this is the power supply connector that is there. Otherwise, you can like use adapter jack as well. So part number is also put here. Okay. Then this is protected by a fuse, and this fuse, after that we have V in A. So V in A is the, let's say 12 volt you are giving. So 12 volt is coming here. So 12 volt to 5 volt 2 ampere is output from this particular switching regulator. Okay. This is also being monitored by this particular LED. So this is a red LED that is going to help you to monitor the like 5 volt output. So whenever the malfunction, like the IC is in malfunction or there is a problem, this reset will go low, and this is how you will understand that LED is not glowing. It means 5 volt is not appearing. Okay. So this is a very nice example of, like utilizing the reset signal to drive a LED. All right. Coming back to the requirement of 3.3 volts. So we have 5 volt here, that VCC is coming, and then a linear regulator is used to convert it to 3.3 volts. So this is there from analog devices, and this is there from ROM semiconductor. Okay. So this is very nice IC that has been like used in various applications for our design. And this particular 3.3 volt is also being monitored through an orange LED. So whenever it is glowing, it means 3.3 volt is proper. If it is not glowing, it means 3.3 volt is not working at all. And after filtering, like through a ferrite bead, we have made it to VDD. Now we needed a reference voltage of 3 volts. So that 3 volt is being generated from VCC, that is 5 volt. So this reference voltage can be used for your DAC reference as well as ADC reference. Coming back to the other part of circuit, so one more part was there which was like a UART to ADC. So let's go into UART to ADC. Alright, so sorry, UART to USB. So what happens is the UART signal that is coming is in C2000 series microcontroller, okay, we have actually SCIA pin, okay, that is capable of having UART functionality as well, okay. So you might not see exclusively UART RX, UART TX, but actually SCIA RX, SCIA TX is actually like supporting for UART RX, UART TX. So those signals has been used here as TXD and RXD signal, and then this is going to get connected to my USB to UART converter IC. Okay, so this is the USB to UART, like bridge IC that is there from Silicon Lab. So USB to UART bridge, what is going to happen is this is going to give you USB positive and USB negative, and then this USB positive negative is taken to a micro USB B type, like USB connector. Okay, and this particular USB line like USB N and USB P is also protected through an ESD diode that is there from Worth Electronics. Okay. So this was all about the like system circuit design that we had to see for this particular microcontroller that we have taken into account. So if you do have any questions or any understanding that is needed for the microcontroller system design and how to do a pin mapping for different peripherals and what is the application that is needed. So what you can do is I have utilized almost all the pin in this particular microcontroller, but your job would be to use as minimal pins as possible because most of the pin can be left unused. Okay, so that is actually a good method. There is no need to like make your design complex or something like that, so that is not needed at all. So whatever is needed, that only you can utilize, and rest of the pin you can leave it open. So how to like terminate your unused pin, that is also there in the microcontroller data sheet that you can have a reference as well. So alright guys, if you do have any questions, put down your questions in the comment box and we shall be able to give you answers. Thank you.